Before we begin, though, there's one of the things that we're experimenting with at Next 18 this year, and that's bringing part of our internal Google culture to the conference. So whenever we do presentations at Google, we have this thing called a dory. And the idea behind the dory is if, hey, sometimes you're sitting in a presentation and a question pops up at the beginning of the presentation, and by the time you get to the end of the presentation, you're like Dory in the fish, where you kind of forget what your question was. So we have people you can put your questions into a portal as you think of them, and then other people using the portal can vote the questions up or vote them down. So I'm going to try, if you're thinking of questions as I'm presenting, put them into the dory. I'll answer some of them at the end, but I will make sure that I answer every question. If not in-house today, then I'll answer them online, so keep the link to the dory itself. The instructions are here on how to use it. You use the app, and you can see the links that you're going to follow there. And then, you put your questions into the dory Q&A. I actually had a couple of questions about an hour ago before the session even began, which I thought was really cool. And so thank you, whoever it was that asked those questions, and I've answered them already. OK, so we're going to talk about machine learning, and there's this ongoing revolution that's happening in machine learning, and because of TensorFlow and because of how we've open sourced TensorFlow, the goal behind that is that you can be a part of that revolution. This isn't something that we're just doing. We've open sourced this platform. We've worked with lots of people. We've worked with lots of partners to build some really interesting scenarios. But any one of these scenarios is something that you can do. And you're not going to require great expertise in machine learning or AI or any of these things. We're democratizing it to make it easy for everybody. But a couple of my favorite examples that I want to share. So first of all is I actually studied physics in university, and back when I was going to university was when they discovered the first extrasolar planets. And how the first extrasolar planets were discovered were by some of the best astrophysicists in the world, and what they were doing was that they were taking a look at stars, and some stars, very distant, very large stars, would have a slight wobble in them. And from time to time, they'd see this star just do a little wobble, and they try to figure out what was causing that wobble. And then they theorized, well, what if there was a really big planet, like a Jupiter or Saturn, orbiting close to that star? Then what would happen is the gravitational attraction of the large-massed planet could cause a wobble in the star itself. And as a result, we discovered the first extrasolar planets, but they were very large planets that were very close to their parent stars. Since then, in the 20-odd years since then, we've discovered thousands and thousands of planets. And just in the last year, through machine learning and through machines being able to spot patterns in the behavior of stars, not only are we discovering extrasolar planets, but we're actually able to see things like in the Kepler-90 system, we're able to count the planets that are in the star. And the Kepler-90I, this planet is a small rocky planet which has got an orbital period of only about 14 days. So it's no longer limited to large planets that are really close to their host star. We're actually being able to map these solar systems, and in the case of the Kepler-90 system, we've actually mapped 8 planets and what the size of those planets are, and then through spectrographic analysis, actually being able to identify some of the materials and the makeup of these planets. Another example is in something called diabetic retinopathy. And diabetic retinopathy is a very common disease, and it can cause blindness and worse if it's not discovered early. And if it's discovered early, it's very cheap and it's very easy to treat with drugs. And some of the machine learning research that we've been working on has actually, through just simple pictures of the cornea, being able to spot some of the markers of diabetic retinopathy, so it can be diagnosed early and it can be diagnosed really cheaply. And now, we're lucky enough, most of us, to live in places with great hospitals like San Francisco. I'm from Seattle and that kind of thing. But there are parts of the world that they don't have access to this kind of imaging equipment. And we think, wouldn't it be marvelous that if someday, and someday very soon, just something cheap like a cell phone, that you will be able to do the machine inference on a cell phone to be able to take a photo of a cornea, load it into a cell phone, and do a diagnosis right away. Things like this we're learning are beginning to revolutionize healthcare. And we found, like some of our results, that while ophthalmologists, some of the most skillful ophthalmologists in the world have like a 99% hit rate in being able to diagnose these things, some machine learning models that we've been building are actually doing the same. They're equivalent and sometimes even slightly better than a human ophthalmologist. Now, the idea here is not to replace ophthalmologists. The idea is to enhance what they can do. If an ophthalmologist can see 100 people in a day instead of 5 people in a day by using something like this, everybody benefits. Another one that I've been really interested in, and I find fascinating, is in understanding and being able to control the deforestation of our planet. And there have been some machine-learned projects have been built where what they've done, and I believe it was in the Amazon rainforest, that they used old Android phones. You know those ones that you're probably going to throw away? And they've been building TensorFlow machine-learned models that will spot the signs of logging. And spotting the signs of logging can actually be very simple. It's the sound of a chainsaw. It's the sound of trees falling. And by training a model with those sounds, by training a model with those things, and putting it onto a cell phone, having that cell phone be connected, and then spreading them through the forest, instead of having people going and trying to monitor to see where illegal logging is going on, these things, once they detect it, they dial home, and it's been cutting illegal logging drastically. Another personal favorite of mine, and this one's a little bit more fun, is being able to use in the Google Arts app, and this you can download and play with on the Play Store right now, is all you got to do is you take a selfie, and then what it will do is, based on the pattern of what it sees in that selfie, it will match your face with famous works of art. Like in this case, you can see here this young lady, she has very distinctive eyes. And she's got a very nice little smile, and her eyes and smile get matched very, very nicely to paintings like this one and this one. And if you try it yourself, it can be a lot of fun. This morning, I decided to sit down and try it out for myself, and I got this. Now, to me, the guy on the right looks more like John Cleese than he looks like me, but I mean, what can you do? But then I thought, maybe I can try to fool the algorithm. So I decided to put a cup of coffee in front of my face, and I got this. So I guess it thought the beard and the cup of coffee looked very similar. So you can have a whole lot of fun with this. And again, it uses machine learning, and the model has been built using all of this famous artwork. And then what it does is, like, when I take a selfie, it matches my face, it extracts features from my face, and it tries to find artwork with similar features, and then it matches me accordingly. But what is machine learning? You come to conferences like this one, you come to maybe Google I/O, you go to AI conferences, and you hear all these great scenarios about finding planets and curing diseases and matching faces with John Cleese or John Cleese lookalikes. But what actually is machine learning? So the way I like to look at it is, if you think about, how many of us here are coders, by the way? How many programmers here? Oh, good. Most of us, okay. So classical programming, when we think about it, is you think about classical programming as a black box, and you put data and you put rules into that black box, and you get answers out of it. So if I were to think about, say, if I'm building something that's like a dog versus cats classifier, that would be really difficult, right? How do you tell the difference between a dog and a cat? Cats might have pointy ears and they're planning to murder you. Dogs probably have long, floppy tongues and they'll love you for the rest of your life. But those things are really hard to do in rules, right? Those things are hard to do in coding. And most of us who are classical programmers, we've used Java, we've used C# or C++ or any of these things. That's what we do. We write rules. If this, then that. While this, do that. All of those kind of things. And then those rules operate on data. We compile them into something of value, and that something of value gives us what we need. That gives us the answers out. Well, all machine learning is, and the revolution around machine learning, is it flips the axis on this diagram. So machine learning is you put the answers in, you put the data in, and you get the rules out. So it may not seem like much, but when you start thinking about some of the scenarios that now become possible, I'm wearing a watch, a smartwatch at the moment, which tracks my activity. This watch knows when I'm walking, it knows when I'm running, it knows when I'm swimming. In my case, probably when I'm trying not to drown. And it can detect all of these things. But think about walking and running. Now, if you're a classical programmer, how would you tell the difference when somebody's wearing a watch between walking and running? Maybe it's based on their speed. You'd somehow be able to infer the speed based on the location of the watch. Maybe if the watch is a heart rate sensor, it'd be based on their heart rates. But some people, when they're running, probably have a much lower heart rate than I have when I'm walking. And how do you tell the difference between when I'm walking and running? That sometimes if I'm going really fast, I might be walking downhill. And sometimes if I'm going really slow, I might be running uphill. So all these if-then become very, very difficult to build something like an activity tracker like I have on this watch. But with machine learning, when you say, OK, I'm not going to write if-then rules. I'm going to give it all of the answers. I'm going to say, OK, we're going to, like, when Apple created this watch and when they've been doing it with the recognition on this watch, they've had thousands of people exercising and say, OK, right now I'm running. Right now I'm walking. Right now I'm swimming. And from that, they've been able to build models. And anybody who builds any kind of activity recognition does the same thing. So now you're feeding into this thing all the answers. This is what walking looks like. This is what running looks like. This is what swimming looks like. And you feed it in the data. This is what it looks like. And as a result, when you build a model around that, then out of that will come the rules. So now in future, if you pass it a bunch of data, it will say, I think you're walking. I think you're running. I think you're swimming. And that's the whole revolution of machine learning. It's not a lot when you think about it. When you look at the two diagrams, they don't look very different. So what I always encourage people to do is think about the scenarios that this empowers. Think about, for example, the planet spotting that I spoke about earlier on. That would not be easy to do with if-then rules. It would be possible, but it's a lot of code that you have to write. It's a lot of code that you have to maintain. And then when you get new data in that breaks the rules, you probably have to rewrite the rules. Think about things like the diabetic retinopathy, the same thing. So when we talk about TensorFlow and when we're building out TensorFlow, we always ask people, just remember this diagram. This is all about you getting your data, understanding your data, getting the answers, that's called labeling the data, and then having a framework that will allow you to munge them together and build something that will give you inference so that you give it future data, and then it will tell you what the class of that data is. So now there's a whole bunch of products that we've built at Google, and you've probably seen a bunch of them this morning in the keynote, and I just wanted to highlight one here. So the idea behind these is that we've been working on this stuff for years. We've been working on how to build something that provides great inference, that provides for great machine learning, and on top of that, we've built some products so that if there's some scenarios that you want to do, like face detection, logo identification, label identification, etc., then there's a product like Cloud Vision that does it, but these aren't different products. Cloud Vision is built on top of TensorFlow. So TensorFlow is the framework that I've mentioned. If you're not familiar with it, it's open source, it's free, you can go download it and you can play with it. And we define it as the machine learning platform for everybody to solve real problems. So I just wanted to set the level of where we're at for this session before I start going into some of the new stuff and what we've been working on in the last year. So here's where we've been going in the last 12 months. So first of all, the number one piece of feedback that we've had from software developers was will you please support my language? I love TensorFlow, I love machine learning, I'm not a Pythonista. I really want to be able to use things such as Swift, or I really want to be able to use things such as JavaScript. And as a result, these are two of the things that we've been working hard to add to the platform. I'm going to be showing some JavaScript stuff later, and I'm also doing a session immediately after this one in, I can't remember if it's upstairs or downstairs, upstairs in the 3000s, and I'll be showing some JavaScript demos there. So the idea is, as a software developer, the JavaScript as a skill is a highly sought after skill, it's a very common skill, and we really wanted to bring the scenarios of being able to do machine learning to JavaScript developers. Because then two things can happen. Number one, you can actually execute models directly in the browser. And number two, you can even train models directly in the browser. There's a really cool demo if you go to js.tensorflow.org where it's a Pac-Man game. And if you've ever seen the Google Doodle of Pac-Man, if you remember that one, you can actually train Pac-Man based on the webcam. So you can point up, point down, point left, point right, and then you can control Pac-Man that way, all done within the browser. So there's no round-tripping of code to Google or anywhere else. All of the training is done in the browser of the model. You're passing it in the answers by saying this is up. You're passing it in the data by frames of your finger pointing up. And then you train the model, and it only takes a few seconds. It's really cool stuff. But this then opens up several different scenarios for machine learning. And the direction that we've been trying to take with TensorFlow is really threefold. So number one, there's TensorFlow itself. So there's the main framework of TensorFlow, and this is designed to allow you to train models and to execute models on a variety of devices. So what that provides you is the APIs and the SDKs and the ability to take the data, take the labels or the answers into that data, compile a model, and then run inference on that model in a variety of places, serving it off of a web browser, et cetera, et cetera. But in addition to that, this year, we've been focusing very hard, and it's part of my core passion, is on something called TensorFlow Lite. And the idea behind TensorFlow Lite is that this is just for executing models and running inference, and it allows you to do it on a variety of devices. So Android, iOS, you've probably seen we've run some demos on Raspberry Pi, and we're working on more IoT devices. We'll have some announcements about that shortly. So the idea here is that sometimes training a model, you need a big, expensive workstation. You need maybe TPUs or GPUs to train something, but you want to be able to distribute that model to people to be able to use it anywhere. Like the diabetic retinopathy I spoke about earlier on, wouldn't it be great if places in the emerging world with a cheap cell phone could just have a simple app with a model running on that app, and then they pass a photograph of the cornea of an eye into it, and then it will run inference on that and give you a a prediction about whether this person has diabetic retinopathy or not. That's the idea behind TensorFlow Lite, to be able to take these big models that you build on workstations, but take them out of the big enterprises, take them out of the universities, and give developers an opportunity to build something that thousands of people use, millions of people can use, and to change the world. So that's our goal behind TensorFlow Lite. Now notice that's just the runtime. You're not going to be doing any training on the devices because they've got relatively less power. And then thirdly is TensorFlow.js. So this is JavaScript. And as I mentioned earlier on, here's a case of now if you want to distribute training to people, so the nice thing about web technology with a web browser, you type in a URL, your application executes within that person's browser. What if you have a scenario where people want to give you data, or you want to train a model off of people's data and off of the labels that they give? You can now distribute the gathering of this data over the web, either train it directly within their browser, or of course have them send it back to you where you can train it by it working in JavaScript. And another nice part about being able to do this in JavaScript is, does anybody use Cloud Functions? A few, or Cloud Functions for Firebase? Okay, so as you know, they run in Node.js. And if it runs in Node.js, now by having JavaScript on there, you can actually execute a function to either run inference on a machine learned model or to build a machine learned model. So think about when you use, the nice thing about Cloud Functions is that they operate off of triggers, where a trigger is something happening in your network or something happening in your system. For example, if a user logs into your application, that's a trigger. And so instead of you explicitly calling a piece of code, you could say, this has triggered this code to execute. And you then may have a scenario where, OK, a user has logged in. I want to run an inference, maybe to do something like a captcha automatically behind the scenes, those kind of things. There's lots of scenarios. It's up to you to kind of think of what would work best for you. So as I've mentioned, one of my passions is mobile. And so I'd like to talk a little bit about TensorFlow Lite. So this is what it's like to use it. So this is Java code running on Android. So if you're a Kotlinista as well, if you like Kotlin, of course this will work in Kotlin. If you're an iOS developer, right now it only works in C++. We haven't built the projections into Objective-C or Swift yet for it, so you'd have to write C++ to do the inference, but we're working on that. But all you have to do is very simply is that there is a package called org.tensorflow.lite.interpreter. And on this one, you would load your model. So earlier I spoke about building a model. You give it answers, you give it data, it gives you rules. You compile that model using TensorFlow. That model from TensorFlow then, to be able to run on mobile, there's a process called flattening, where the idea is you take that and it flattens it, and it makes it more compact, and it removes some of the larger floating point operations and stuff like that, makes it smaller, so it will run on a mobile device. And the file extension for that is .tflite, which is why you see here, new interpreter, awesome model.tflite. And then all you have to do with that is you pass it your inputs, and it gives you back the outputs. So for example, I don't know, if you're writing a classifier like I mentioned for diabetic retinopathy, your input would be your image, or how you've processed that image so that the model would recognize it, and your outputs that it would give you back would be a probability of this person having that disease. Excuse me. The performance of TensorFlow Lite is actually really nice. As you can see here, we did this benchmark, and there's famous machine learning models called MobileNet and Inception, which are used for image classification. And when we flattened the model, when we ran it on TensorFlow Lite on an Android device or on an iOS device, and we did some benchmarking in Q1 of this year, these are the performance increases that we've actually seen. So the orange bar is running it on TensorFlow on a traditional workstation. The gray bar is running it on TensorFlow Lite on a mobile. And we can see that inference is very, very fast. And I'm going to show a demo in a moment of me doing a live image classification, and you'll see how fast it will actually execute. Actually, I'll do it right now. So if we can switch to the demo machine. So I need to sign in, sorry. OK, so I'm actually going to run this in the Android emulator, which I know is incredibly brave of me, live on stage. So as you'll see, it's so I'm running the Android emulator here, and you can see the webcam on the Android emulator is going, and it's actually classifying three things. So what's happening is this is MobileNet has been trained with 1,000 different images. So there's a neural network that's been trained to detect 1,000 different types of image. So what happens is now every time it's capturing a frame from the webcam, or from the front cam on the emulated phone, what it's actually doing is it's passing that to this compiled model. This compiled model is coming back then with a set of probabilities of each of these 1,000. So like right now, I'm not showing it a banana, so it's setting it a probability of like, less than 0.011% that it's a banana. And then I'm taking the top 3 that it actually gave me back and then representing them. So, we have this grid on the wall behind us. Obviously, it hasn't been trained for that, but that kind of looks like a strainer. And as a result, it's saying, hey, that's a strainer. And as you can see then, above that 1385 milliseconds, that's the amount of time it's taking to do the inference. But consider that that's actually running on the emulator on my desktop as I'm speaking. What, did it say something funny? Sometimes it says like Dachshund or something when I step in front of it. Let's see. I'm an Italian Greyhound. Yay! I wish I was that fast. But like if you're familiar with Silicon Valley and the hot dog, not hot dog thing, I don't know how it will work in this light, so we'll see. But this is my famous banana demo, but let's see if it says it's a banana. There we go. 100% probability that it was a banana. I had to put this behind. I was cheating. So that's like the MobileNet model is a famous model amongst researchers. They've taken 1,000 images. We've built this neural network that can then classify amongst those 1,000 images. Strainer, shower curtain, and all those are 3 of those images. Banana and Italian Greyhounds are others. And this is now running on Android, as you can see here. And it's doing pretty well. It's only taking like 1,100 milliseconds to actually identify something when running on an emulator. I also have this running on I have a Pixel 2 phone. I have it running on my phone. If you see me later and you want to see a demo of how fast it is on actual hardware, that it can do this inference usually in 50 milliseconds or less. So if we can switch back to the desktop, please, or to the slides, please. I'm a keyboard, I'm a sock, I'm a strainer, I'm a running shoe. Yeah, can we switch back to the slides, please, before I embarrass myself further? I'm a hamster. So the next one that I mentioned, so remember there were 3 runtimes. There's TensorFlow, there's TensorFlow Lite, and then there's TensorFlow.js. So TensorFlow.js, the idea is that we've been working hard. We released this in March of this year. And we see the 2 main scenarios for this is, number 1, to be able to do training or inference within the browser. It takes advantage of things such as WebGL when it's running in the browser, so it can be very, very fast. And then on the other side of it, if you have servers and you want to execute stuff on a Node.js server, be that in something like a Cloud Function or just your own Node.js server, then you can do so as well. And the really neat thing, like I've mentioned about this, and I know I'm repeating myself, but it is really cool, is the fact that you can do both training and inference. So you can actually present somebody with a web page, they give you data, and it will train a model based on their data. And then they can execute inference on that. Or you can build a model, such as the MobileNet model that I've mentioned, which was the one that I just used for the image classification, download to that browser, and then retrain the final layer of that with classifications of their own. And that's how the Pac-Man demo works. If you go to js.tensorflow.org and take a look at the Pac-Man demo, that will be trained with 4 new classes of image, 1 for up, 1 for down, 1 for left, 1 for right. You can do it however you like. I tend to use my finger for training it, or some people will actually look up, look down, look left, look right. And while it's a fun little demo, think about the impact that that could have on things such as accessibility. Sometimes we build accessibility into products, but the accessibility tends to be a common solution for the I don't want to use the term lowest common denominator, but you know what I mean, for the mass denominator in this case. But there might be for an individual, the accessibility might work differently. Maybe they want to scroll by going like this. Maybe they want to scroll by going like this. I don't know, or scroll by nodding their head. That you could actually use an image classifier in the browser, retrained in the browser for different classes, like say scroll or click or something like that, so that accessibility could be customized to a particular user. These are the kind of scenarios that are now becoming possible. We can't build them all. We can't even think of them all. And that's why we like to talk about TensorFlow with folks like you, that I know there are people in this audience right now who've got fabulous scenarios, and they just haven't had the tools with which to build them. And we're hoping that the tools that we're building will unblock you from being able to do that. So coding. So perhaps the biggest changes in TensorFlow, as well as adding this new stuff, is in some of the coding that we've been able to provide. So if you've been a TensorFlow developer up to now, and you are a developer rather than an academic, if you've come from a development background, then the coding of TensorFlow models might have seemed a little alien to you. The idea was you define a model, you end up doing something called building a graph, and you build everything ahead of time, and then you execute the graph to do the training. You know, as software developers, I don't know about you, I can't write more than 3 lines of code without having a bug in it. And as a result, I like to write code 2 or 3 lines at a time, run them, test them, write the next 2 or 3 lines, run them, test them. And that's traditional programming. And that didn't really work very well with TensorFlow. So we have something that we put into TensorFlow that, which I'm going to show that. Actually, I went to the last one first. We put something into TensorFlow that we called eager execution. And the idea behind eager execution is what that gives you is the ability to be like a pure Python programmer, but continue to build TensorFlow models. You get things such as step-by-step debugging. You get the immediacy of being a real Python developer. And then also, as you're building your models, if you're familiar with things such as gradient descent, and there's differentiation in math that needs to be done to determine loss and all that kind of thing, you don't lose that. There's something called a gradient tape in there, and based on the name tape, if you're from the VHS world like I used to be, you know, the idea is that's recording everything on tape, and that tape you can go back and forward and all that kind of stuff. So it's like you're not losing any of the value that you had by when you were building graph-based stuff by changing to immediacy because things such as a gradient tape are there. But let me skip back. So the other big change, and to me the other really exciting big change, is in how you build models. So we've been working really closely with Keras, and Francois Choyer, who invented Keras, now works for Google, and he works on our team. And so he has been bringing Keras to TensorFlow in the tf.keras namespace. And if you've done any construction of neural networks, if you've done anything like that, and you want to get into the really complicated stuff, the idea behind Keras is that it makes it really easy. Now, some of the terms that you see on the slide here, if you're not a neural network person, may seem unintuitive to you, and I'm really sorry about that. But the idea, when you think about it, when you define a neural network, generally you're defining layers of neurons, and then in each layer of neurons you're defining behaviors. And in those behaviors, there's generally 2 things that you define. One is called an activation function, and this is what it takes to actually activate that neuron and how it behaves when it is activated. And the other one is called a loss function, and this is what type of function am I going to use to minimize loss in this layer. If you're not a neural network person, sorry, a lot of that would be kind of gibberish to you. But the code to do this was actually very complicated before Keras. And with Keras here, here's how I can now define a neural network. I'm defining it, and it's just like, hey, I'm creating a sequential network. So I have a number of layers, and they're operating in a sequence. Here's my shape of my input, 28 by 28. You know, my first layer of my network, well, this is what it's going to be. It's a convolutional, 2-dimensional one. And my activation in this is something called a ReLU. And I'll continue to define my network like that. This kind of code, to be able to find a network like this, it might have taken dozens, if not hundreds of lines of code previously. But with Keras, as you can see, if you're a neural network person, it's intuitive to you. If you are just learning this for the first time, a lot of these terms will seem very difficult to you, but it'll actually, as you start learning and as they start growing in it, you'll see that this is actually really simplified it for you. Think about it in terms of object-oriented development. You're creating an object, which is your sequential neural network, and you're setting properties on that. You're saying, this layer looks like this, has this function. This layer looks like this, has this function. And it's really as simple as that. Then there's input processing. The most important thing when you're defining a neural network is you've got to feed it good data. If you remember my diagram earlier on where I said you give it data and you give it answers and it infers the rules, you got to give it good data. You know, garbage in, garbage out, or if you remember Johnny 5, need input. So it's like, so being able to give it good data, you need to be able to have the tools to define your data and to take dirty data that you might have and clean it, or to have tools to take data that you have and do things like normalizing it or making it easier to understand for neural network. And then also, more importantly, if you're building giant neural networks that take a lot of training, as you're feeding data in, you want to be efficient. If you feed in a terabyte of data and then wait 100 hours for it to train, and then you have another terabyte of data and you wait 100 hours for it to train, that's not very efficient. So there's a concept called data pipelines, where you can optimize your input of data to the time that it takes to train the data. And we've been building that out in something called the tf.data namespace. So instead of you just taking random data in a data structure like NumPy or lists in Swift or something along those lines, if you actually take your data and you format it with the tf.data namespace, it's synchronized with the training, and as a result, you can make your input of data and training pipeline much more efficient. So eager, I've mentioned earlier on. And so now the next thing is we've been working really hard on these things called cloud TPUs. So T in TPU stands for tensor. So the name TensorFlow comes from the flow of tensors through a network, and tensors are a way that you can define your data so that they're optimized for neural networks and for neural networks to process them. So we said we wanted to build a chip that's designed specifically for processing tensors. And that's why we came up with this thing that we call the TPU, the tensor processing unit. They are highly, highly, highly optimized for TensorFlow. And as a result, you can see some of the data about this here. You know, it's high bandwidth memory. There's 180 teraflops per device, which apparently is quite a lot. But I'd rather look at the results. Oh, sorry, before I go to them, I like to kind of use an analogy for that. So think about when you're training a neural network on your laptop or on your desktop PC, that probably has a CPU. And a CPU, the idea behind that is that's a chip that's designed for processing anything. Right? It's designed for managing the windows on your screen. It's designed for your networking stack. It's designed for all of these things. And it's a little bit like a Swiss Army knife. You know, it's designed to be able to do everything, but it's not particularly optimized for anything. So as a result, it's not optimized for training and machine learning. And maybe you want to build a model, and that model might take you a month to build on a CPU, or it might take a year, depending on the amount of data that you have. So the idea with the TPU is that it's a highly optimized, highly focused knife. It's like a sushi chef's knife. So if you've ever known a sushi chef, or if you've ever sat at a bar where the people are making sushi, they have these highly optimized, highly sharp knives that they can use to cut the fish without like taking bones and all of those kind of things with it. And I always like to say, like, you know, people go, why would I want to use a TPU? Why would I want to pay for a TPU? And think about it in those terms. If you need to train a model and you've got a lot of data to train that model on, like the thousands or hundreds of thousands of hours it takes to do something like activity recognition on a watch, you want that training to happen quickly and you want it to be optimized for actually training that model. And so I always like to say, well, if you're going to use a CPU, you're using a Swiss Army knife to make sushi, which you don't really want to do. So taking one common model called ResNet for image classification, here's some of the results that we got from using a TPU on it. So the number of images per second being fed in using TF data were about 2,700. And synthetic images, so the idea was like you take in the real image, we do some processing on that to make a synthetic image, and then they were being fed in. It was over 3,000 per second. And we found that we were able to train it to 76% accuracy. So that is when you do the classification like I was doing earlier on, it's right 76% of the time on ImageNet. But doing this on a tensor, on a TPU, on a tensor processing unit, the cost for doing this was actually about $85. When we did this. Now compare that, like if you were to buy a GPU, or many universities were renting access to GPUs, the cost was it used to be in the tens of thousands of dollars, it brought it down to the thousands of dollars. There was one experiment, and when we designed this slide actually for a presentation that Jeff Dean was giving back in April, and we put it with $85 on there. And before he went on stage, somebody did another test, and they actually had it significantly lower than that. I'm not allowed to say the number, but the point is it's actually going down sharply. So think about building a really, really complex model. You're talking about now it can cost in the tens of dollars instead of in the thousands or hundreds of thousands of dollars. And if you take a look at this link, you can actually see the benchmark submission that we put in at Stanford. So some of the other things that we've been trying to do is that, as TensorFlow, it's moving towards version 1.10 very soon, is that it's now time to bring more developers into the fold. It's becoming less of an academic infrastructure and academic framework, and we're trying to make it more and more developer-friendly so developers can start building real things with it. Things such as the cell phone that I spoke about and scenarios with that one. And as a result, we launched a blog on blog.tensorflow.org, and we launched a YouTube channel. I personally run the YouTube channel, so if you've got any ideas for videos or any questions, you'll see me all over that one, and please, reach out. I'm happy to create any videos for scenarios that you want to see and you want to learn about. Also, what we've been trying to do is to empower everybody to learn and explore machine learning through something called the Machine Learning Crash Course. And it's this link at the bottom here, g.co/machine learning crash course, is a place where you can learn it. And not trying to be salesy about it or anything, but this was the course that we built to train us. So I learned machine learning. I used to work on Firebase at Google. I learned machine learning while I was on the Firebase team using the internal version of this course. So this is what we've used to train the actual Google engineers who are building the thing. So some other things that we've been working on, TensorFlow Hub is the next one. So if you think about models, that there are common scenarios for models, like image recognition or translation or text classification. So we said we want to be able to create a hub where people can download those models and use them, and maybe even use parts of them in their own models. If you're familiar with TensorFlow, a lot of the models that we've done, we've just put on GitHub. And GitHub is great. You can download like a model off of that and you can use it. But it's not optimized for something like this. It's not like a catalog. It's not searchable. It's not easy for everybody to share in one place. So the idea is that we wanted to build TensorFlow Hub, or TF Hub as we call it, so that you can find models that you can reuse, you can find models that you can build on, or of course, you can share your own models. And again, it's at that URL, tensorflow.org/hub. So one of the things that's kind of coming in the future, we're still working hard on it, that we're really passionate about now, is what we call learn to learn, or AutoML. And the idea is we said, okay, well, what if today you want to build a solution? What do you need? You need machine learning expertise. You need people who understand Python or whatever the language I was talking about earlier, whatever language I was talking about earlier can do. You need them to be able to understand the data, how to format the data, put that into pipelines, how to design a neural network. There's a lot of expertise. Of course, you need all the data, and you also need the computation power. This is what the world looks like today if you want to build a good solution. We said, well, what if we could take the deep ML expertise out of that and just say data plus lots and lots and lots of computation? Because machine learning, after all, is you feed it in the answers, you feed it in the data, and it comes up with an inference from it. So if you remember this slide that I showed you earlier on, I've been working on TensorFlow for about 6 months. I still don't understand half of the words on this slide. Not many people do. I don't know why, for example, I would use a max pooling of 2222 instead of 3333, other than a lot of experimentation, a lot of trial, and a lot of error. There are people who can understand a neural network and understand the math behind a neural network and who maybe write better code than I would here. But a lot of the time when I'm building something like this, it's a lot of trial and error. It's a lot of, okay, where am I going to flatten it? Where am I going to do dropouts? Where am I going to do all these kind of things? And there's a bit of a black box element in designing these neural networks that, you can take a look at. There are academic papers coming out on a daily basis that say, well, if you want to do image recognition, you should do this many dropouts, or you should do that many dropouts, or you should use a ReLU, or you should use something else. It's not as prescriptive as, well, in many ways it could be. I was about to say, it's not as prescriptive as writing typical code. But then sometimes, well, is it better to do a for loop? Is it better to do a while loop? Or, these kind of things in typical code. And it's the same kind of thing that will happen when you're designing neural networks. Should I design it with this number of input layers or this type of function? So we said, well, what if, this kind of code, instead of a human doing a lot of trial and error behind that we actually have a computer do the trial and error behind that? That we say, okay, we know roughly what our neural network should look like, and we know roughly what kind of activation functions should be on there and what kind of dropouts and all that kind of stuff. And what if we then say, take that and then train on that, but then we try lots of different ones? We change the function here, we change the design of a layer there, all these kind of things, and we iterate and iterate and iterate, and then we evaluate those models. Then we could actually have a computer learning how to learn. We could actually build a machine learning kind of thing that learns how to learn. Now, the computational expense for this is really, really big right now, which is probably why Google are the only ones doing it. But with Moore's law being Moore's law, it's getting cheaper over time. And as a result, we can actually start thinking about in the future of building neural architectures that optimize themselves. So some of the results that we've had out of this is that when we take a look at some of the handcrafted models that are out there that have been built by some of the world's greatest researchers, if you take a look at the x-axis here, the x-axis here is the number of operations of computation that are needed. Just see that as the expense, ultimately, even though that expense is coming down over time. And the y-axis is the accuracy and precision of these image recognition models. So if we take a look at something like Inception, which you can see in the lower left, that's a very cheap and very easy model, and the accuracy of it is around 70%. Or MobileNet, which is the one that I was using when I was classifying on my phone, you can see it's a pretty cheap model, and the accuracy is about 70%. But when we start looking at all the research that's been done on this, and we go all the way over to the right, so you can see the cost of that is orders of magnitude higher, but the actual accuracy isn't. It's going to 80% or 82% instead of 70%. So we said, okay, what if we can compare a network that learns itself rather than something that was designed by a human to this? And this is what we got. So when we started training on small models, as you can see on the left, we actually knocked things like MobileNet and Inception out of the water. So for the same cost, we had far more accurate models. And then when we go over onto the right, we're in the same ballpark, if not slightly better. So for really, really large data sets and so instead of 1,000 images, maybe 100,000 images it's able to classify, we've been able to find that, we're in the same ballpark by having these networks, instead of a human designing this network and testing this network and figuring it out, that the human gives us the base that we're going to start from, but then it learns and it improves itself over time. And if you remember the AlphaGo, and that beat Lee Sedol, the champion, but then there was another version of AlphaGo which learned by itself that beat the one that beat Lee Sedol. It's the same kind of technology that was in use there. So just going back to it, some of the impact that you can have, and we've been working on it and Learn to Learn as well for the diabetic retinopathy as well. Again, comparing with humans, taking like humans and the data that humans have been able to give us to train a model, but then using Learn to Learn to improve on that model. That's where we've been getting the results in diabetic retinopathy that are actually improving on the top over what the top ophthalmologists can do. And again, I just want to reiterate, this is not a replacement for ophthalmologists. The goal here is that if an ophthalmologist can manually do this and see 5 people a day, but if they have a tool like this that allows them to see 100 people a day, everybody wins. So with that in mind, just remember, the whole goal and the whole revolution of machine learning is you think about, you put your answers in, you put your data in, and you get your rules out. And as a programmer, if you're switching that pivot from what you've done, it opens up these massive, massive new scenarios for you that you can provide value for yourself, for your business, and for the world at large. So that's our goal with TensorFlow, and that's what we've been working on in the last year. Our goal ultimately is to make machines intelligent and to improve people's lives.